I believe that diatomic hydrogen is transparent and that there is a lot more of it in the universe than the experts think. So much of it, in fact, that I think it is the complete explanation for the dark matter in the universe which causes galaxies to rotate faster in the outer arms than one would expect based on the visible matter. When I was arguing for this point on ResearchGate, I was directed to a paper by Farajabeen Islam called The Formation of Molecular Hydrogen in the Interstellar Medium. In section 1.2 of the paper, I found something that the author says was a typical exchange reactions involving hydrogen. A couple of these seemed to me very surprising. One of them, the first, was that one might have a hydrogen with 2 electrons, and the other was that there might be ionized diatomic hydrogen, that is 2 protons and 1 electron, as stable states. Now, that these states might exist, I cannot say, but for the paper to make reference to such things without any source or explanation, as though they are not at all surprising, this made me a bit suspicious. Then we go into section 1.3, and here we have the reaction that I expected to be commonplace. Okay, it's in section 1.4. 2 hydrogen atoms come together to form an H2 molecule and release a photon. However, the author says that the direct radiative association of hydrogen atoms is highly inefficient. At the low pressures in the interstellar medium, the author continued, there is just not sufficient contact time between the hydrogen atoms to radiate away its binding energy of 4.5 electron volts before it is likely to dissociate. Now, this strikes me as completely backwards. I almost get the impression that this author believes that the radiation time is directly correlated to the energy. That is, it sounds like he's saying that it takes a longer amount of time to get rid of a larger amount of energy. Of course, exactly the opposite is true. A typical equation for this is the time-energy Heisenberg uncertainty principle, which says that delta E delta T is greater than or equal to h bar. So the minimum amount of time that it's going to take to get rid of 4.5 electron volts of energy will be 6.58 times 10 to the negative 16th electron volt seconds divided by 4.5 electron volts is 146 times 10 to the negative 18th seconds. Now, another way to think about how long it would take to dissipate 4.5 electron volts of radiation is by the Planck-Einstein relation, which ends up with a very similar formula. The energy of a photon is equal to Planck's constant times the frequency of the photon, which would be let's do h bar times 2 pi, and then the frequency is 1 over the time, or the amount of time that it takes for the for that photon to go through the space, or for a whole wavelength of the photon to go through a space. So this we will go ahead and put in, solve this for delta t. Delta t equals 2 pi h bar over E, which is essentially this value multiplied by 2 pi. So this is the amount of time for 1 radian of the photon, or the wave, to go by. So, and this is for the entire photon to go by. So 1 radian would be something like right there. The whole photon is right there. So this is 918 times 10 to the negative 18th seconds, or about approximately 1 times 10 to the negative 17th seconds. And so that is more than enough time for 4.5 electron volts to dissipate. So back to Farajabeen Islam, he's saying that there is a 10 to the negative 8th probability per second of combining. Now, if I had done this calculation here and it had come out something like 10 to the 8th seconds, then I would totally agree that there was no more than a probability of 10 to the negative 8th per second for the particle to combine. But with the probability being closer to, or with the delta t being closer to 10 to the negative 17th second, I think that the probability per second is about 100% per second. Per second of what, you might ask? Well, per second of being in close proximity. Now, Farajabeen also says this thing, that the vibrational oscillation in the molecule is typically only 10 to the negative 13th seconds. Now, the period of vibrational oscillation is kind of an absurd thing to be concerned about here, because we are, of course, supposed to be wondering how long the two atoms are in close proximity, not how fast they're vibrating. Basically, this entire argument is completely nonsensical, and I referred to this on ResearchGate as Farajabeen's argument because, well, regardless of the original source, he is the one who has stuck it into his book. But I was told by George Dishman that this is not Islam's argument. It is taken from a standard textbook, which he then provided a link to. And while this is not available online, I was able to find it in the Western Illinois University Physics Library nearby. The text was called The Physics of the Interstellar Medium by J.E. Dyson and D.A. Williams. The text is called The Physics of the Interstellar Medium by J.E. Dyson and D.A. Williams, and many of the words and numbers that Farajabeen Islam used also appear in section 3.4 of this text. However, to claim that the argument here is the same as Islam's argument is false. For one, Dyson and Williams are not referring specifically to hydrogen atoms, but to typical atoms, I guess, A and B. So they do refer to the time of in contact being very short, and they compare that time of contact to the period of vibrational oscillation in the molecule. I don't know why they compare those two, but one should not take from this that the two are equal. It should be clear that Dyson and Williams are essentially just picking numbers out of thin air here and not talking about any specific atoms or molecules. They say the largest transition probabilities are usually about 10 to the 8th per second. Again, this number seems to come from thin air because they don't hint as to how they calculated it or what specific pair of atoms they were thinking of when they did calculate it. But it should be noted that Farajabeen wrote a transition probability of 10 to the negative 8th per second, whereas the referenced text has a transition probability 16 orders of magnitude higher, of 10 to the 8th per second. After George Dishman told me that it was not Farajabeen Islam's argument, I said, I'm not sure if it matters where the argument comes from, except in some cases it might be interesting to see exactly where the miscommunication or misconception arose, but what matters is that it is false. To say as a general rule there is not sufficient contact time for the excited hydrogen molecule to radiate away its binding energy of 4.5 electron volts before it is likely to dissociate, it's a false generality regardless of who made the error. And I think it is interesting to note that factor of 10 to the 16th in when they have a difference between 10 to the 8th and 10 to the negative 8th. I think it is interesting to see where that misconception arose. It's also interesting to see how this little addition, the time of contact is the time of contact is comparable to the period of vibrational oscillation in the molecule. These is kind of an irrelevant, really the period of vibrational oscillation in the molecule is sort of an irrelevant topic here, but they kind of stuck that in there, and it seems like that confused the author of the other paper, who thought that the period of vibrational oscillation was a relevant issue here, or a relevant quantity. George Dishman suggests that I start looking at the textbooks and examining the source for information. This clearly has been what is taught in undergraduate classes for at least 2 decades. Egad, I hope not. It says, if you can show the calculations are in error and solve a problem nobody else has cracked, you'll be famous. And I'd said I'd be very surprised if there were any calculations in the reference text regarding the matter, since it can't be supported by any basic principle, but I'll see what I can find. George Dishman responded that scientists don't just pluck numbers out of thin air. But this thing right here, consider 2 atoms, A and B, without making a distinction of what those atoms are, saying the time of contact is very short, and kind of making this note, it's comparable, and then just deciding since it's comparable, you'll use that number. And then saying usually. Now, I think it's very clear from the context that Dyson and Williams here were exactly pulling numbers out of thin air. I don't object to that because they're just kind of thinking through things without any specific examples. But when you go and try to take that kind of general method of reasoning for general atoms, that you need that time of contact, you need to figure out what that time of contact is, and you need to figure out the transition probability and how long it takes to radiate energy. Compare those things. That's just a general method for figuring out how many of the particles will manage to form binary molecules. So I would agree that scientists don't often pluck numbers out of thin air, but in this situation, yes, they did. So I don't fault D&W or Dyson and Williams for that. I see that Farajabeen Islam, well, got this off by a factor of, or by 16 orders of magnitude, and he kind of misrepresented misunderstood their argument, because he thought that they were, when they said typical, or basically molecules A and B, and that they were talking about two molecules of monatomic hydrogen. But on the next page of Physics of the Interstellar Medium, I think I see something that could almost be called an error. It says here that the mean interstellar ultraviolet flux in the wavelengths shown in figure 3.3 provides about 10 to the 10th 10 billion photons per meter squared per second. of any given nanometer wavelength. Now, when I first read that, I thought, wow, 10 billion photons in each of those wavelengths from 120 nanometers to 190 nanometers? I thought, wow, that's got to be a huge amount of energy. However, when I did a calculation to discover exactly how much energy we were talking about, I found out that it was only about 10 microwatts. Here, kilogram meter squared per second squared is a joule, and I was thinking about in terms of each second. The equation for the energy of a photon is hc over lambda, and I have 10 billion photons of each energy, and I wanted to make it go from 120 nanometers to 190 nanometers. So I found out that was about 10 microwatts. But remember, Dyson and Watson claimed that this 10 microwatts is the mean amount of ultraviolet intensity to which all interstellar gas is exposed. In order to check that, I wanted to get an idea of the intensity of the ultraviolet radiation the Earth gets from the Sun. The average amount of solar radiation received by the Earth's atmosphere per unit area when the Earth is at its mean distance from the Sun is equal to 1,370 watts per square meter. So you can think of it like this. We have a distribution of many wavelengths of light, all coming from the Earth from the Sun, coming to the Earth from the Sun. This is a histogram where the vertical axis represents watts per meter squared per nanometer, and the horizontal axis represents nanometers, and the area under this entire curve is 1,370 watts per meter squared. The peak of this histogram for the Sun is somewhere between 400 and 700 nanometers, the wavelengths of visible light. Now, the region of concern here is radiation coming from the Sun between about 120 and 190 nanometers. But as a matter of fact, we can go all the way down to 0, which would be infinite frequency or infinite energy photons. And it's not going to make much of a difference to the amount of energy because most of it is going to be in this section here. Now, the formula for this curve is called the Planck distribution equation. And this formula will give the intensity of the light at each frequency as it comes off of the surface of the Sun. The radiation at the surface of the Earth would be this value times the surface area of the Sun divided by the area of a 1 astronomical unit sphere. Now here's the calculation I did yesterday. I started with the surface temperature of the Sun in SI units, 5800 Kelvin. I gave hbar, h, and c in SI units. This hbar is 1.05 times 10 to the negative 34th joule seconds. H is 2 pi times hbar. C is 3 times 10 to the 8th meters per second. And I created the formula for the Planck distribution, wrote it in there. And then I said the total power, this is the total power that you get from the entire spectrum of the Sun from 0 to infinite wavelength. So I'm integrating as lambda goes from 0 to infinity. Part of the power, I did another integral. This time I went ahead and calculated all of the frequencies from 0 to 190 nanometers. can see I'm using SI units, so I'm going to go ahead and give that as 190 times 10 to the negative 9th meters. The UV exposure, I need to change that to 1370 watts because I had 1300. I'm going to have 1370 watts times the part of the power that is given in ultraviolet frequencies divided by the part of the power that is given, the total power that is given off by the sun entirely. It turns out to be 1.196 watts. Now this is much bigger than the 10 microwatts that Dyson and Williams said was the mean interstellar UV flux in these wavelengths. Sorry, it's 1.26 watts now that I adjusted the calculation. But the question is, what does it mean to say the mean interstellar UV flux in these wavelengths? Because there's really nothing average about Earth's position in the galaxy. Earth is not in interstellar space. It is extremely close to the nearest star compared to the average random point in space. So while Earth's thermosphere might be exposed to 1.26 watts per square meter of ultraviolet light of wavelengths less than 190 nanometers, I would like to know where we can find a spot where there is only 10 microwatts of ultraviolet light per square meter. For this, I considered that luminosity is proportional to the inverse square of the distance. The luminosity at the 10 microwatt distance is proportional to the distance of the 10 microwatt distance, and the luminosity at the Earth distance is proportional to 1 over the Earth distance squared. And because of the proportionality, all of the proportional constants will cancel, so I can say the luminosity at 10, we can say 10 microwatts divided by 1.26, was it 1.26? Yeah, it was 1.2606 watts is equal to, I'll flip those, so it's distance of 1 AU, which is 1 AU, 1 astronomical unit squared divided by 1, or distance at the 10 micro watt distance squared. So I can solve that for the 10 microwatt distance, which is going to be the square root of 1.26 divided by 10 times 10 to the negative 6th. Comes out to be 355 astronomical units. Now, how in the world did I put a 2 in there the other day? I have no idea. But if I take it away, I have 369 astronomical units. I multiplied that by 206,000 astronomical units per parsec and 3.26 light years per parsec, and it comes out to just over 6/10, or just less than, just a little over 0.5% of a light year. I think it is notable that the Oort Cloud is supposed to be like 50,000 astronomical units, and most hydrogen gas is assumed to be beyond. Most interstellar gas is considered to be outside the Oort Cloud. So if this number is accurate for the distance to the Oort Cloud, well, let's use 5,000 because this says occupying a distance between 5,000 and 100,000 astronomical units. So let's say that most gases will start to appear at 5,000 astronomical units because that's the region that's cleared out by the solar wind. Then we'll be doing this calculation again with 1.26 here. The luminosity we are trying to find, we'll use 1 astronomical unit squared here, and we'll plug in the distance to the Oort Cloud here. And from that, I end up with L is about 50.8 nanowatts per square meter. So this is at the Oort Cloud. And if you assume that most of the gas of the universe, most of the interstellar gas lies in regions outside the Oort Cloud of their respective stars, which I think is a reasonable assumption, then you could say that the average gas is subject to a radiation, an ultraviolet radiation level of 50.8 nanowatts per meter squared maximum. This would be a pretty high estimate for the amount of ultraviolet radiation that gas is exposed to. Okay, well, sorry if this was a bit long, but I think that wraps things up. Hope you enjoyed watching, and have a nice afternoon.